Let's be honest. Have you ever stared out an airplane window and caught yourself thinking that your ancestor and a stagecoach might have gotten to the resort not that much slower? I'm joking, of course, but only partly. From the moment the Wright Flyer first sputtered into the air, its engine roar barely louder than a modern lawnmower, we were gripped by speed fever. 100, 300, 500, 800 kilometers per hour. It seemed like just a little more and we'd be having breakfast in Paris and lunch in Tokyo. Progress was moving faster than a fighter jet on afterburner. But then something clicked. Imagine a sprinter who makes a powerful burst off the starting line, only to slow down halfway through the race and settle into an economical jog. From the sidelines, it looks like they've almost stopped, even though they're still running very fast. That is the perfect metaphor for commercial aviation today. The numbers speak for themselves. Over the past half-century, the cruising speed of a passenger airliner has been stuck at 800 to 900 kilometers per hour. Yes, the Boeing 787 or Airbus A350 are technological marvels, woven from carbon fiber and packed with smart electronics. But in terms of speed, they are barely any faster than the Boeing 747, which was carrying passengers back in the 70s when your parents were listening to vinyl on cassette tapes. So, what happened? Did we hit a wall? Here's the paradox. We didn't. We consciously hit the brakes. It turned out that the race for speed is just one factor, and far from the most important one, in a giant equation called global aviation. Why did we stop rushing? The answer isn't a single reason, but a puzzle pieced together from economics, the laws of physics, politics, and even human psychology. This is the story of why flying faster is terribly unprofitable, how the sound barrier became not just an engineering, but a commercial failure, and why airlines today are fighting not for minutes, but for extra kilograms on board. Ready to figure it out? Fasten your seatbelts. We are cleared for takeoff.
Imagine you're a passenger on a flight in 1928. You're not squeezing into a narrow seat, but stepping into a cabin that feels rugged and industrial, with its corrugated metal walls and 3 roaring engines just outside the window. You're aboard the Ford 4AT Trimotor, affectionately known as the Tin Goose. For its era, this aircraft was the height of modern travel, a flying testament to American industrial might. Its cruising speed of about 150 kilometers per hour, or 90 miles per hour, wasn't just acceptable, it was revolutionary. This was the machine that convinced the everyday American that flying was a viable, if not yet comfortable, way to get from one city to another. But here's the question that might strike you today. Why does that revolutionary speed seem so painfully slow to us now? Even 2 decades later, with the iconic propeller-driven airliners like the Douglas DC-6 and Lockheed Constellation, the sleek, pressurized Connies that crossed oceans, speeds had only climbed to around 480 to 550 kilometers per hour, or 300 to 340 miles per hour. So in over 20 years of development, commercial speeds had barely tripled? Were engineers just not trying hard enough? The truth is, in the first half of the 20th century, the primary goal wasn't to go faster, it was to arrive reliably. Range, payload, and crucially, safety were the holy grail. The Ford Trimotor wasn't just an aircraft, it was a statement. Its 3 engines meant it could, famously, fly on one if the others failed. It could carry 12 or more passengers on nascent airline routes, bouncing through the weather in an unpressurized cabin, but it landed safely, time and again. Speed was a secondary concern to survival and establishing a trustworthy industry. The sky was being conquered not by velocity, but by durability. And now you might be thinking, okay, propeller planes, understood. But then came the jet age. That had to be the real leap. And you're right about that. The debut of aircraft like the British de Havilland Comet in 1952 and the Boeing 707 a few years later was a cultural and technological shock. Passengers weren't just flying faster, they were experiencing a new mode of existence.
They sliced through the air at 800, 900 kilometers per hour, leaving the bumpy, noisy world of propellers behind. It seemed like the start of an unstoppable acceleration, a future where transatlantic flights would soon take minutes, not hours. But history, as it often does, had a different lesson to teach. The jet age didn't open the door to infinite speed. Instead, it drew a line in the sky.
Close your eyes for a moment and imagine it's the 1960s. And humanity isn't just dreaming of reaching the moon, but of conquering the skies with passenger planes faster than sound itself. This was more than a technological race. It was a geopolitical duel, a clash of titans played out in the stratosphere. In one corner, the sleek, arrow-like Anglo-French Concorde. In the other, the Soviet Tu-144, a symbol of communist engineering prowess. The Tu-144 made its first flight on December 31, 1968, beating its rival by 2 months, and in June 1969, it became the first passenger aircraft in the world to break the sound barrier. For a glorious moment, it seemed the future was already here. And what a future it was! While conventional planes trudged along at 10-11 kilometers, these speedsters soared at the edge of space, reaching altitudes of 18-19 kilometers. Passengers didn't see the familiar blue sky outside their windows, but the deep black of the cosmos and the glitter of stars. A flight from London to New York was slashed from 7-8 hours to just 3.5. You could take off at sunset and, thanks to time zones, land before you left. This wasn't travel. It was a form of time travel, an exclusive experience for the privileged few. But as is often the case, this radiant dream had a brutally pragmatic and expensive underside. Supersonic speed came with a supersonic price tag. These aircraft gulped down fuel with an insatiable appetite. They were thunderously loud, shackled by noise restrictions that limited their routes. Their maintenance was fiendishly complex and costly, and a ticket cost nearly as much as a new car. A popular anecdote even claimed that at cruising speed, the Concorde's fuselage would expand by 20 centimeters due to heat, and passengers were warned not to touch the windows. They'd burn their fingers. This wasn't mass transportation. It was a luxury item, a statement. The dream ultimately collided with the hard wall of economic reality. A catastrophic crash of the Tu-144 at the 1973 Paris Air Show dealt a severe blow to the project's reputation. The USSR ceased passenger operations by 1978. The Concorde endured longer, until 2003. But over 27 years, it carried just over 4 million passengers, a drop in the ocean compared to any conventional airliner. A modern Boeing 737 can move that many people in a matter of months. In the end, the supersonic dream wasn't felled by physics, but by finance. The mass market voted with its wallet for efficiency, affordability, and range, not for breathtaking speed. The era of supersonic passenger travel was brilliant and breathtakingly short, like a shooting star that blazes across the night sky, leaving behind a trail of legends and a lingering question: will we ever dare to try it again? For now, the Concorde and Tu-144 stand as majestic museum pieces, reminders of a future that arrived too soon.
Let's be honest, if speed were the top priority, we'd already be commuting across the ocean in a couple of hours. But imagine if your car, upon increasing its speed from 100 to 110 kilometers per hour, started guzzling 25% more fuel. Would you still drive it like that? Exactly. Aircraft operate on the same principle, only their appetite for fuel is on a cosmic scale. The rule here is simple and ruthless. The faster you go, the more you pay. And this isn't a linear relationship, it's exponential. A mere 10% increase in speed requires the plane to burn roughly 25% more fuel. This isn't due to airline greed, it's pure physics. At higher speeds, the air becomes a near-solid wall, and punching through it is incredibly costly. Let's look at the numbers. An ordinary Boeing 737 drinks about 2.5 tons of jet fuel per hour in the sky. Its bigger brother, the wide-body Boeing 777, consumes up to 8 tons per hour. And the legendary jumbo Boeing 747 surpasses 10 tons for every flight hour. Now consider the supersonic luxury of the Concorde. It was a true racing car of the skies, but with a matching appetite. Per passenger, it burned 3 to 4 times more fuel than a conventional airliner. That's why a ticket wasn't just expensive, it was a status symbol, like buying a private island today. You might object, but what about the USSR? The T-144 flew, and its tickets were cheaper. True, but that was the famous Soviet price tag. The state simply subsidized each of those flights, masking their real astronomical cost. The routes remained massively unprofitable, and behind that curtain, the economics were never sustainable.
And now, let's bust the biggest myth. You'll find online theories that airlines intentionally slow down their planes to save money. Well, there's no conspiracy. That comfortable cruising speed of 800 to 850 kilometers per hour, or Mach 0.85, is the sweet spot. It's the optimal balance engineers, economists, and pilots have found between fast and financially viable. When fuel can account for up to 30% of an airline's operational costs, every extra ton of kerosene burned means dozens of tickets that would have to become more expensive. We fly at this speed not because we can't go faster, but because otherwise air travel would be an elite privilege, not a mode of mass transport. This isn't slow. It's economically brilliant. And now for the most important life hack you didn't know about. Even though the plane could fly faster, the pilots don't let it. Why? Because airlines use compromise modes. Your Boeing or Airbus's cruising speed isn't its maximum speed. It's the most economical speed. Calculations show that slightly reducing speed by 30 to 60 miles per hour, or 50 to 100 kilometers per hour, drastically cuts fuel consumption, increases engine lifespan, and lowers the total cost per hour flight. Those extra 15 minutes you spend in the air save thousands of dollars on everyone's ticket price.
Here are just a few reasons why it's better not to chase speed. Fragile giants. It turned out that flying faster than sound wasn't just about pushing the throttle. When transitioning to supersonic speed, the aerodynamics change dramatically. The center of pressure shifts, and a 188-ton liner starts behaving like an unstable aero. To keep it balanced, they had to pump tons of fuel between tanks mid-flight. Imagine that system operating on every single trip. The safety margin was lower. While a regular plane can handle turbulence with load factors of up to 3.5 Gs, the Concorde's limit was just plus 2.5 Gs. One shark maneuver and the structure could fail. Runway extreme. A normal plane accelerates to about 155 to 175 miles per hour, 250 to 280 kilometers per hour for takeoff. The Concorde needed to reach nearly 250 miles per hour, like speeding a sports car down a wet runway trying to get airborne. And then they had to stop this behemoth on a standard-length runway. The problem was solved by using a brake-by-wire system for the first time in commercial aviation, a precursor to modern systems. Without it, the plane would have simply overshot the tarmac. Complicated? You bet. Invisible threats at altitude. The cruising altitude for supersonic flight is 59,000 to 62,000 feet, 18 to 19 kilometers, which is practically the edge of space. And this is where one of the most serious dangers lurked, the risk of rapid decompression. At that height, there's almost no air, and if a crack appears in the fuselage, oxygen would be sucked out instantly. An emergency descent from 60,000 feet isn't the same as from 30,000 feet. It's a complex procedure that risks the airframe and the passenger's health. A thunderous wake.
A sonic boom isn't just a bang. It's a powerful shock wave that rolls behind the aircraft along its entire flight path, causing complaints from people on the ground and even shattering windows. The Tu-144 was a real king of noise in this regard. Because of this, supersonic flights over land were heavily restricted, which negated their main advantage, speed. Even if planes could fly at fighter jet speeds, the airport's operational system would remain the same. A modern hub is a giant, living organism where everything follows a rigid rhythm. Runways, aprons, jet bridges, refueling, and baggage loading services, every element is a cog in a clockwork mechanism. And if you spin one cog faster, the whole mechanism breaks. The takeoff queue. At major hubs like Frankfurt or Heathrow, planes form air traffic jams. Delays for takeoff or landing can reach dozens of minutes. Imagine, your airliner races to New York an hour faster, but loses all that time circling in a holding pattern over the destination airport. The total travel time for the passenger remains unchanged. There's an ironic joke among pilots. You could fly at the speed of light, but the suitcases would still arrive later. And that's the bitter truth. The speed of baggage loading and passenger boarding has become the bottleneck of the entire system. The sky is not a boundless ocean. It's more like a complex multi-level interchange with rules, traffic lights, and controllers ensuring thousands of cars don't collide. Air corridors and altitudes. Planes don't fly in a straight line. They move along strictly defined routes. Air corridors, like trains on tracks. These corridors have their own traffic capacity. Navigating no-fly zones, politics, military exercises, dangerous weather phenomena, all this forces airliners to take detours. The fastest route from a physics standpoint is often unavailable from a logistical and safety standpoint.
And here's the first paradox. Civil aviation isn't flying as slow as it seems slow because that's more comfortable for your brain. Have you ever wondered why, after takeoff, the most dynamic phase, the flight turns into a smooth glide, almost like being in an elevator? It all comes down to a lack of visual reference points. On the ground, the rapid blur of trees and poles unmistakably tells your brain, we're speeding. At 10 kilometers high, outside your window is a static void. There are no points of comparison and therefore no sensation of speed. Your brain quickly adapts and accepts the current state as the new normal. After an hour in the air, you could be flying at the speed of sound, and it would also start to feel ordinary. And this brings us to the main point. Airlines aren't selling speed. They are selling comfort and predictability. Think about it. What would you choose? Save an hour of flight time but endure shaking and stress like on the supersonic Concorde? Or spend a bit more time in the air but in a comfortable seat with stable Wi-Fi and a hot cup of coffee? The vast majority of passengers, even those in business class, vote with their wallets for the second option. Research and industry practice show that people aren't willing to pay many times more for speed if it comes with discomfort. Their top priorities are taking off on time, being able to sleep or work peacefully, and landing without delays. Speed alone has long ceased to be a luxury or a competitive advantage. It has become a utilitarian function, optimized for peace of mind, not for adrenaline.
But it seems like everything is changing. The supersonic dream, buried along with the Concorde and the Tu-144, is experiencing a rebirth. And this isn't just nostalgia, it's a technological reboot with new rules. Imagine a flight from Moscow to Tokyo, not in 9 hours, but in 3. From New York to London, faster than that episode you didn't have time to finish during the flight. Sounds like science fiction? Think again. What's changed? Everything. First, the technology. The new projects aren't just fast machines, they're smart ones. For instance, the Moscow Aviation Institute is developing an airliner that can climb to an altitude of 22.5 kilometers and reach speeds of around 3,700 kilometers per hour. That's 3 times the speed of sound. But the key thing is that it will be 3 times more fuel efficient than its legendary predecessors. How? thanks new composite materials and intelligent systems that optimize the flight in real time. Second, the legislation. Until recently, supersonic flights over land were banned. Who could forget those thunderous sonic booms? But in 2025, the U.S. lifted this decades-old ban. The key condition, the aircraft must not produce a sonic boom. And this is where NASA and private companies like Boom Supersonic take the stage. Their Overture project isn't just a concept anymore. It's a real machine for 64 to 80 passengers capable of flying at Mach 1.7. So what's the catch? Of course, there are still challenges. The main curse of supersonic flight has always been its appetite: fuel, noise, emissions. Today, ecology isn't just a trendy word, it's a hard requirement. New engines must not only be powerful but also quiet, and their carbon footprint minimal. And here begins the most complex engineering race: how to combine the incompatible, speed and sustainability. Russia, the US, China, and Europe have all joined this race. In Russia, for example, they plan to create a flying technology demonstrator by 2027. But experts are cautious. Mass supersonic travel won't be possible before the 2030s. Why so long? Because it's not enough to just build a fast plane. Its operation needs to be profitable for airlines, comfortable for passengers, and acceptable for the planet. So what's the final verdict? Supersonic aviation is making a comeback. But this isn't the 20th century race for records at any cost. Now the bet is on sustainable development. We're learning from the mistakes of the past. Speed matters, but not at the expense of everything else. The new generation of supersonic airliners is a symbiosis of power, intelligence, and responsibility. So pretty soon we might be choosing our tickets not just by price and airline, but also by speed, economy, comfort, or supersonic. And the time we save in the air might just become the new currency in a world where every minute counts.